Okay, cool. Thank you, Dennis. Yeah, so my name is Bill Baxley, and I'm the Chief Engineer of the Ocean Energy Program here at FAU, which I'm going to be talking to you about today. Please note, I'm an engineer, not necessarily a scientist, and so I'm going to be talking about more of the practical aspects of doing this stuff out in the ocean and the practical effects of weather on the equipment. And I might throw one or two equations in just because it's kind of a requirement. But mostly, I'm just going to talk about the practical aspects of things, okay? And so like Dennis said, I was with the Navy for 16 years, came here to Harbor Branch, and worked with the ships and the submersibles and all the engineers here. And once that transitioned, we started really focusing more on this ocean energy using the Gulf Stream offshore. So that's what I plan to talk to you about, as well as some of our assessment efforts and some of the, and try to hopefully educate you on a few of the more obscure aspects of ocean engineering. So, assuming this will work, there we go. So what is ocean engineering, right? Okay, it's a combination of almost all type of engineering. So you have mechanical, electrical, civil, acoustic, and even chemical engineering. And so you learn how to take all that sort of stuff and apply it to a very harsh environment, which is the ocean, right? And basically with that level of knowledge, we then go out as design engineers and we try to meet the requirements of scientists here at Harbor Branch, so and other customers, if you will. So if they need to get a certain fish or a certain piece of coral from a certain location, we come up with a way to get you down there to get the equipment and get it there safely and accurately. And that's essentially how the JSLs were developed, and a lot of the other equipment over here that we have at Harbor Branch is they are the enablers of the scientists to go out and get what they need. Okay, so it's very, very exciting. And in addition to the science and the educational aspects of it, the part I like about, which I'll show you some of it, is you're out in the field, you're out on the deck, you're out dancing with the devil, right? Because when you're on the back deck, you have large equipment, you have, the seas can be rough, it's a fairly hazardous environment, and you have to really know what you're doing, and you have to be very careful and focused on what you're doing to still have all of these and be up here and able to talk to you guys. So that's what ocean engineering is, at least from my perspective. I've been doing it for 30 years, and it's awesome. So I would recommend anybody that wants to change careers, go be an engineer. All right, so now we'll get into the administrative stuff. So we're the Southeast National Marine Renewable Energy Center. We got the 2014 worst acronym in the world, SNMREC. I don't know how they came up with that. But anyway, so we're one of 3 ocean research centers. There's one out in Hawaii where they do waves, and OTEC, which is Ocean Thermal Energy Conversion, where they bring cold water up from the deep, and they do some heat transfer up near the surface where the water is warmer, and they can make electricity that way. And of course waves, because that's where all the surfers are. And then out in Oregon and Washington, they're working together with waves, because again, they have the Pacific and the large waves out there, and tides, because the higher you go on the planet in latitude, the larger the tides are, because you're further away from the equator, the tidal bulge, and it tends to pull the water. So you have larger tides than we do down here in Florida, which are only maybe a meter, but usually less than a meter. Now down in here in Florida, we're doing ocean current because we have the Gulf Stream, which I'll go into a lot of detail about. But we're also, it's not necessarily OTEC, it's not taking cold water and converting it with the warm water, it's more cold water air conditioning. So if you can pump cold water from out deep and go into a refrigeration system, you don't need Freon and compressors and energy and all that sort of stuff. So that's kind of what we've been looking at down there, down in South Florida, but we're focusing at the moment on the ocean current energy. So these are just some of the roles as an engineer, design, build, test marine renewable energy systems, manage data collection equipment, which I'll talk about, conduct surveys, not only for the design, but regulatory, right? There's always regulatory when you work in the ocean, and also the researchers, such as the people here at Harbor Branch and FAU. And then to support customers and facility users once we establish our test facility. So, cool, the audio working. So, just for those of you not familiar with the motion in the ocean, this is a NASA animation of the currents and all the other turbulence, if you will, in the ocean. You can see here the Gulf Stream, right, or the Florida current, which is where we are. These are the loop currents you may have heard about out in the Gulf of Mexico. But then there's all these other ancillary currents and turbulence all around out in the ocean And it just gives you an idea of just how much kinetic energy or energy of motion is out in the water. That if we could harness just a very small percentage of this, then we'd have we'd be all right. So this is a viewless current. This is off South Africa. That's another current that we're looking at, and I'll talk about that a little bit more. And then as we come up along the coast of Africa here, there's a few currents in this area, but there's really three main ones that I'll talk about. But again, this is just to kind of give you an idea of just how many ocean currents are out there. So of all the currents on the Earth, we have Japan, the Kuroshio, we have the Gulf Stream right here off southeast U.S., and we have the Agulhas on the south of Africa. And so this is what we're focusing on right here. And again, they're near major load centers, right? So it's where people need power, especially South Florida. There's a huge need for down there. So what this shows is the profile of the velocities between the Bahamas and the coast of Florida. And if you'll notice, it's shifted to the west. It's called a western boundary current. And so as the Earth turns, there's the Coriolis force that tends to make things go off to the right. As the Earth turns and as these gyres, the water flow, it tends to push them up against the coastline. And that's why you see it's kind of like if you swirl in a bathtub, the water kind of piles up to one side. The velocities do that here. So that's good for us here in South Florida because we're on the correct side to access this. If it was in the Bahamas, we'd have a long way to go to get to it. So it's a western boundary current, and the currents are close to the surface as well. And about 8.5 billion gallons of water every second flow through the Straits of Florida. So that's a tremendous, tremendous amount of water going through there. And if you're ever out there anchored in it, or you're holding station in it, it's just unbelievable how much water is flowing past you every second. So this is a yearly profile of the velocities throughout the water column. So this is the surface, and you see during the summer, when the water's hotter, because it's a thermohaline circulation, which means it's based on water temperature and water salinity, haline. So in the summer, the water's warmer, and you get higher flows, and that's what these reds show. Whereas throughout the rest of the year, you still have fairly good flow near the surface, but it's not as pronounced as in the summer. But what this also shows is that the velocities, again, they're near the surface. Down near the bottom, there's really no flow down there. And this just shows that there's actually about 20 gigawatts of power available, but I only put on here 5 gigawatts because nobody's good enough to get every bit of it. At least I don't think so. I'm certainly not. But anyway, so there's about 5 gigawatts available that we can do, and that's about 20% of Florida's energy needs. So as with all renewable energy systems, you need to look at it as a tool in a toolbox, not the solution for everything, right? Because if you have a hammer, what does everything look like, Jimmy? A nail, right? So whereas if you have different tools, you can use them for different applications like solar, maybe wind, just not off our beach, and then the ocean flow, right? I remember all those signs. Okay, so what about everybody always asks me, okay, well, but what's the stability of this with global warming and all this other stuff going on? So these are 3 studies, one from '84, the STACK study. This was based on a cruise ship that went back and forth between the Bahamas and Miami for a few years. And this was these crazy guys in 1890 out in a sailing ship. They actually anchored their vessel at different points in the Gulf Stream and lowered these mechanical little whirly things that would drop steel balls every rotation and counted the velocity. It was really cool. But what's interesting is even though over 100 years ago, the essential character of the flow is the same, right? You still have this western boundary, this western intensified flow, and it's all about the same magnitude. So, of course, this is again, it's not a scientific statement, but it's a practical statement. It looks like it's been the same for about 100 years or so, right? So there's no smoking guns, if you will, that it's really changing quickly. So that's one good thing that we're not having to plan on a rapid change of this, at least not based on historical data. Now, speaking of the government, which I wasn't, but I am now. So the government owns everything, right? So offshore, they have these offshore lease blocks. So if you want to do anything out in federal waters, which is out past 12 miles in most places, then you need to rent some real estate from them. The Bureau of Ocean Energy Management. It used to be the Minerals Management Service until the oil spill, and then they changed the name to protect the guilty. I'm not supposed to say that, but it's kind of how it worked out. But anyway, so there's these blocks off the coast, and if we want to put anything out there to test, we need to do that. So these are a zoom in off of Fort Lauderdale. This is Port Everglades and our CTEC campus down in Hollywood. So what we did is we went out and we chose these 3 blocks here for our project. Because I don't know if you're familiar with wind farms, when they have all these wind farms out there, if they put them too close to each other along the wind direction, they start to trip each other up, right? The flow is disturbed one or the other. And so that's why we got these 2 blocks. This is 6 miles in length, so we could go out there and test this out based on modeling. And then it goes east-west because the velocities are slightly higher in this one than in this one. So we can learn to walk here before we learn to run and move out into the deeper water. So in order to do that, we had to go out and characterize the bottom and see what critters live down there, what habitats and that sort of stuff. And so one of the ways you do that is with multi-beam sonar. Okay, so as the ship moves along, it sends out acoustic beams in a fan, and as they're reflected back, you can indicate the depth, and here it's shown by color. So you can go out and instead of like a regular fish finder you may have with just one point everywhere you are, we call it a swath. So you just go out there, and it's called mowing the lawn. You just go back and forth, and you just cover the whole area with sonar, and you can get a really detailed picture of the bottom in bathymetry. And this is what the coverage is that we did. Remember the blocks I showed you going east to west? We started with those. And then when you take that and you convert it into 3D, you get this cool perspective view showing this is the escarpment. This is about a 1,000-foot drop, kind of like this, right off the edge there. And then these are various habitat maps that Nova Southeastern University did for us down in Hollywood. And it just tells you what type of organisms may exist in those type of bottoms, right? And the highest density is right out here where it does go over, because as with any flow stream, as the water's coming by, it's going the fastest through that channel, right? So it's always, that's where the fastest is, which means it brings the most food to any organisms that are out here, up through the Gulf Stream. So again, we chose to work up here on the terrace to be not necessarily in the core of the flow, but be in high enough flow and be far enough away so we're not disturbing the bottom and that sort of stuff. So, so once we then mapped out the area, now we have to characterize again the resource, right? So looking at 100 years of Gulf Stream data is good if you're just looking at general trends, but if you need to design a device, you really need to know what's happening on a daily or hourly basis, right? So we go out, and this is called an acoustic Doppler current profiler. So it has these 4 heads on here, 4 sonar heads at a 20-degree angle. So they shoot sound up at different angles from each other, okay? So like, think of it in the old World War II spotlights that they used to, put up in the sky. Like war movies. So what is the Doppler effect? It's basically, if you send out a sound of a specific frequency, it goes out and comes back, whatever it reflects on, if it's not moving, it's the exact same frequency, okay? Whereas if you send it out and it reflects on something, like say a piece of plankton moving along, the reflected sound will be shifted. It'll either be a higher pitch or a lower pitch based on the direction it's going, okay? So, and you can measure the amount of frequency change, which is shown some here. I told you there'd be a little bit of math. If you show the frequency change, then you can determine the velocity of that piece of plankton or seaweed or whatever is going by, and you can actually measure the velocity of the water with sound instead of having to put little propellers on there like they used to do back in the day, okay? And everyone knows what the Doppler shift is when you hear a race car go by or a fire truck go by. Anybody want to make that sound? No, that's the siren going. No. Well, since no one ever wants to, I have it on here. It's going to be loud. All right, so that was the Doppler shift. So you see as it's coming towards you, the pitch is getting higher, right? And then it drops as it goes away. Well, if you can accurately measure that, you can determine exactly how far that car or that plankton was going. And that's what we do with an ADCP. So you can measure how fast something's going, and the reason that you have those four, what we call orthogonal transducers, two going that way and two going that way, is because depending on the speed difference in this direction versus the other direction, you can get an actual, what's called a vector. You can get the speed it's going and the direction it's going based on your device, okay? And that's how we got all those cool red and blue plots and everything, because not only does it show how fast the water is going, but the direction it's going, which I'll show you here in a second. So anyway, so that's how the whole Doppler ADCP system works. So we use those extensively. We usually put 4 or 6 out at a time to cover an area because we want to see what these hourly changes are in the velocity. This is where we grow them. So these are about ready for picking. No, not really. I was just getting this ready. It kind of looks like it, though. If I'd have turned it around, it would look better. But anyway, and so this, again, this is a typical type vessel we take offshore to deploy these things. Now, this video, this video is how not to do it, okay? Because the crane operator wasn't exactly familiar with handling this sort of thing, and that's why I was saying you're dancing with the devil, right? Sometimes the devil's the crane operator. Sometimes it's a 4,000-pound buoy. But in any case, you're out there and you just got to really, and I don't think I've got too much yelling on here. So I think I bleeped most of that out. Let's see. Okay, so now the buoy, you can see we're pulling it behind the boat, and it's got the anchor, and now I've got the release here that's going to drop it. So we're getting the boat over position.
What?
Because see, she was supposed to say drop instead of okay, we're cool. I'm like, what was that? I mean, give me a definitive, you know. So we have think of taking a car, right, on a ship moving like this, and you're going to lift it 20 feet up into the air, right? Well, it has a lot of motion, and it's really hard to restrain that much mass rotating, you know, spinning that or swinging that high. You need to keep it low, and so you keep it only about 6 inches off the deck, so that if something does happen, he can just drop it really quick, and it'll hit the deck and stop. Yes, he did, but he didn't next time. That's what I was trying to say. And she said drop the next time. Okay, so we put these down, and they're about 15, 20 feet off of the seafloor in 1,000 feet of water. And because of that Doppler effect, you can measure the whole water column, right? With sound, you can measure the whole thing. And so this is how it's supposed to release. So this is called an acoustic release. You don't have to go down there and physically cut a line or anything or send a submarine or a diver. So you send a sound pulse down. The release hears it. It opens. And then the whole buoy, because it's buoyant, pops up to the surface. And then all you're left with is an anchor, or the railroad wheels on the bottom, which eventually, based on our permit, we're going to have to go pick all these up. So we redesigned those for being able to be picked up too. But anyway, so that's how it's supposed to go, right? Well, sometimes it doesn't always work. So we put an ADCP out in 2009, discovered it was missing in 2010. I just want you to know I didn't start till 2012 with the program. And so then it was found in the Azores, out in the middle of the North Atlantic over here, in 2013. And I said, I'll go get it. So flew out there and I took all the equipment off. Now, it's only like a very small plane that flies to the Azores back and forth, prop plane. And so we couldn't bring a lot of stuff back. So I took the guts out of all this, and the University of the Azores got a really nice buoy and a bunch of aluminum housings and stuff. So it's also a trip of goodwill. So anyway, so that's, and This is why. Because remember I said an ocean engineer also has some chemical engineering in there for corrosion, right? So you really need to know the types of materials you're using, the corrosion problems, and dissimilar metals. When you put two different metals together, sometimes they don't like each other, and they corrode away, and it leads to failures and losing equipment. So, and when something's nice and shiny, when you first put it in the water, it doesn't mean it's stainless steel. It just means it's nice and shiny. So you really need to know what you're doing, right? Okay, the other thing that we use are CODARs. They're coastal ocean radars. And what they do is they send out radar waves, but they use that same Doppler shift I was telling you about, but at a radar frequency to measure the velocity of the wave tops as they move along in the Gulf Stream. So we can actually, with the ADCPs, measure the water column, and with the CODARs, we can measure what's going on in the actual surface, the upper meter of the water. So and all this is important when you're trying to design something because, again, we're not interested in why all this stuff is happening. We're interested in the extremes of what's happening so we can bound our design, right? So we can design it, whatever it's doing what it's doing, my thing can survive whatever it's doing, right? The maximum and minimum that we can find. So this is what I came up with for presentations like this, as well as for my own use, just figuring out how to visualize how these currents are going. So each one of these is a vector of the water going forward. And you can see the vectors are shorter near the bottom, right? And they're higher near the surface, just like we saw in all of our plots. But this just gives you an idea, and each of these are independent measurements, so it just gives you an overall feel of how the whole water column is going, and you can get, you can get an idea of the magnitude and the changes. And more importantly, what I'll show you is during hurricanes, what the hurricanes do. And then this is the CODAR. I don't know if you can see the little black dots, but they're virtual messages in a bottle. So we put them in the output, and it shows us how the surface of the current is really changing. So, the Gulf Stream is sometimes called a river in the ocean, but it's not necessarily a river in the ocean. It's a meandering nightmare sometimes. But it generally goes to the north, but there are these variances and again, we have to design for that to know what's going on. The software also works with some tidal data that we got from Fort Pierce. So it gives you a really clear understanding of the going in and going out, right? And then since it's shallow, the velocities are pretty much the same because all that water, if you've ever been to Fort Pierce Inlet, all that water is trying to run out that small inlet, right? Well, it doesn't have a chance to what they call stratify and faster water near the surface. It's just trying to rush out as fast as it can. And that's what these type of animations are supposed to do, is show you that the water is just going in and out as fast as it can. Okay? So, why worry about hurricanes? Because death, taxes, and hurricanes, right? It's going to get you. Especially if this is your workshop, right? Right here. So, you got to plan for them, and so in that case, you have to measure for them. So, when Sandy went by in 2012, even though Sandy stayed far offshore and then eventually visited up here, they're about 500 kilometers offshore here, but by having a storm that large with that persistent wind that really started affecting us about here, to this whole swath here, those waves just constantly coming in at a fixed angle caused this on our CODAR. So it's kind of hard to see because it's an older version of the software, but you see all the water surface is going this way except for this big eddy right here in Fort Lauderdale, right? And I don't know if I was down there at the time, but A1A was eroded down there because we had a lot of erosion right there at up near Hillsborough and north of Fort Lauderdale. And we had it at our CODAR site too. So the reason that data stopped at midnight on the 10th or whenever it was is because the whole CODAR system was eroded away. And so a $150,000 system just went out with the beach. And this was like over 200 foot wide beach, and it was just gone right back up to the seawall. So, yeah. So we went into ruggedized mode, right? And so we ruggedized all of our equipment. We moved it behind seawalls. We buried all the conduit. We put all these anchored systems in, and we also added some weather systems so that we can know what's going on and monitor the storms for the next time, which was very helpful when Irma went by. Okay, so this is when Sandy went by. Now, notice normally the water's fast up here, and when the wind is blowing to the west, it's strong. But when the wind switches, like it does in a hurricane, look what happens to the surface, up near the surface. It really it really knocks the velocity down, and then it starts to twist. See how it almost goes to zero near the surface, right? And this is the water level, the difference between predicted and actual levels in Port of Miami. So when the Gulf Stream basically stopped, all that water, it's like people trying to get out of a burning building, right? Once it stops, there's a lot of backup behind you, and all that backed up into Fort Lauderdale and Miami and all the other places. So this is some of the stuff that we monitor. But the main thing is, a lot of these devices, which I'll show you, they're like kites in the water, right? Because remember, the high velocities are near the surface. There's no flow down near the surface. And it's 400 meters or 1,200 feet of water. You can't just put towers out there in the ocean, right? So they're almost like kites. So they're going to have to fly up near the surface to generate their power. Well, when the current goes to zero near the surface, what's going to happen if it's only lift supported? It's like a kite when the wind stops, right? Right down to the bottom. And you can say, oh yeah, but it'll come back. But by that time, your kite is now on the ground where there is no velocity. So it could be raging again up top, but now there's no lift force to get it back up, right? So that's something that we're working on too. And I'm using my interns and stuff for figuring some of this stuff out because their minds are younger than mine. Okay, and then this is looking from the top, and this is the other thing. So these are the two ADCPs out deep, and even though their magnitudes are changing, remember it's magnitude and direction, even though their magnitudes are changing, they're still going to the north, which is good because we don't want a flow reversal. Well, if you come into shallow water, this is some Navy data that we had from 130 meters, they're just spinning up, they're spinning like tops, right? And so it's much better to have your devices out in deeper water because the flow is always going to the north. We've almost never found it where it goes to the south. But in shallower water where it'd be easier to work, the flows spin around, right? And another way to look at that, this is called a progressive vector diagram. So all I'm doing is adding those vectors up and making these little lines here. So by doing that, you can really see where these rotations are happening, right? Instead of watching the arrows and trying to cross your eyes, you can really see where the rotations are happening on this ADCP data. So that's good for hurricanes, but it's also good, if you'll notice, down near the bottom, see how much shorter the red line is than the purple line? Well, that's really important if you're looking at transport of like nutrients or pollutants or something, right? So you can look at this data and actually see that if you have a surface oil spill, right, it's going to move really quickly, whereas if it's on the bottom, like we had out in the Gulf, it doesn't move nearly as fast as up here where you can readily measure. So you need to really consider that in a lot of your planning to keep this vertical stratification of the currents going to know how to address that sort of thing. We're not, but the data is available for people that are interested in that sort of thing. All right, and we're not going to use any oil, so we don't have to worry about it. Okay, so, and just really, really quickly, just the only other math thing is the Ekman spiral. So what that does is if you have the wind blowing on the surface of the water, the current is actually 45 degrees to the right. And that's based on the Coriolis effect and a bunch of other things I won't get into. But the cool thing is that the net transport, or the current that's generated by a high wind, is 90 degrees off. The water goes 90 degrees to the flow. And that's why I think during Sandy, remember how the wind was blowing to the west and the water sped up? Because when the wind was going to the west, it was adding water to the north, pushing the current faster, right? Well, when it came around to the east, now it was pushing water back against the current, and that tended to back it up. So that's one of the things that we're looking at, because it's a lot easier to have a bunch of weather stations on the surface than to have a bunch of ADCPs down there monitoring your equipment. You know what I mean? So we're looking at ways to not have to have underwater things to monitor all of our equipment. Does that make sense? Okay, cool. And then this is just a profile when Sandy went by. So this is the high velocities during the storm, and then a few days later we get zero velocities. And I think that's, again, because of the backing up of the flow, and then it rushes forward, and this is the backing up portion right here where the velocity goes to zero. So if you had a kite in this area, it'd be flying fine here, but then it would just drop, and once you get down into this low velocity area, you're stuck, right? And this just shows the direction, and there's really no direction change in Sandy. So then Irma comes along. Everybody remember Irma? Probably. Okay, so Irma was just cruising along here back in 17, and we weren't quite sure when it was going to make this dog leg. Remember that? We weren't quite sure if it was going to do that or when it finally came over like that. Okay, well, I had already evacuated my house and my kids up to here. And so, but I wanted to measure the storm, right? And so I threw an ADCP together. I got some crazy boat to go out with me. So this was on the 6th, like 2 days before the storm got here. Took it offshore. We went all the way out, 20 miles out in the core, dropped it down, came back, and this was the calm before the storm as we were coming in, right? That wasn't the bad part. This was the bad part, right? It's like in The Walking Dead, and when they're going into Atlanta and all the cars are coming out. That's maybe be a little, sorry. But that's how I felt. So I was going this way, right, with all this equipment, and all these people were just flooding out of South Florida. So fortunately, we went out, put it out, and I came back up A1A, so I didn't have to deal with any of this. But the worst part is that my wife, who happened to be in Peru at the time, she called my son, because all she's seen is the Weather Channel in Peru, right? She calls my son and says, "Where's your dad?" "Oh, he's out on the boat." Wrong answer, right? So train your kids better. So anyway, so then she was really mad at me. I'm like, everything's cool. The kids are safe. Don't worry about me. So anyway, but we got some really good data, right? So this is Irma, filmed at my mom's house as it was coming in, and it missed us, but you can see all this onshore flow that was really changing things. And so, so since it's been a few years, I added color. And so this is the velocity. So the reds and then the blacks are the highest velocities. But again, it gives you the idea that the lower velocities are down below. But up top where you need it, they're really variable, and they can really go down if you have a device that's up there. And then this is looking at it from the top view. But the good thing about during Irma, well, if there's a good thing, is that it continually went to the north. It didn't spin back or forth as well. But we really got some fast velocities, and then you can see where it all goes to blue here for just a little while. And again, that's when all your systems would crash if they were only lift-based. This is the surface from our CODAR. You can see these big eddies, whereas normally the flow should be going straight. And this is an animation of our radars. So this is before the storm. It's pretty much going straight. There's a little bit of bouncing, and that's where my ADCP is I put out. But then as the storm gets closer, the winds start to affect, and it starts to really affect along the shallow regions, right? Remember, it's the shallow areas that are mostly affected because of that Ekman forcing. And then right when things started to get interesting, Miami shut their power down to protect all their switchgear, right? So we lost all of our power in our measurement systems, and we didn't get data through the storm. So now we're working at getting these really big UPSs like you put on your computer, except they're bigger than this. And we're going to put those out so we can get the full storm next time, because it's very important. Because as you can see, this was a storm, and then this was that. It wasn't as long, but it was still a drop in velocity. And you can see the change in direction here. There was quite a bit more during Irma. And there's various reasons for that, and I have a paper if y'all want to read it, but I ain't going to go into it right now. So it was kind of cool. So I talked to this other guy, and he said, well, what about the transport of the Gulf Stream, the overall total flow of the Gulf Stream? And there's a cable that goes from West Palm Beach over to 8 Mile Rock in the Bahamas. And by just the nature, just by the salt water flowing over this electrical cable, it can induce a voltage into this electrical conductor, right? It's kind of like the Earth's biggest electromagnet. So, and what they can do is based on it's kind of like with the Doppler effect. Instead of the change in frequency, the change in that voltage is how much water is actually flowing through there. All right? Not in a small point like we're interested in, but the entire flow. So if the voltage changes, you can measure how much the total flow is changing, right? Like in a river. And so I looked at that, and this is through the year, it's pretty stable, right? But during the hurricanes, it really dropped. It went from around 30 down to 17 million cubic meters per second. And then during Irma, first it went up a little bit, and then it dropped down. It only went down about 8 million cubic meters per second. And so there was an effect on here. But again, since we're looking at the equipment, we're looking at the very specific stuff, okay? So this is the dream that was sold to the state and to DOE in 2008. So see how awesome and utopian this is, right? So we got all this stuff out here just generating power away. We're all happy. And so that looks awesome, right? Well, when I came along, right, and, oh, here, this is what you got to do. I'm like, well, this is what it reminded me of, right? Back in the old magazines, like, oh, we're going to be out in space and have space stations and nuclear powered. You know what I mean? It's kind of fanciful, right? I was like, wait a minute, let's crawl before we walk for sure, much less run. And so this is what we came up with instead. A single buoy where you tie a boat to it, and you put a generator down, and you can test how well it's working and everything. So that's the concept that we came up with to start with. And this was back around 2012 or so, as we started working on that deployment. And that's what all this other work has been going towards. So here's some various energy approaches from other companies. So this is some of the stuff that we're supposed to assess. So we have a large array of things up close near the surface. This is ours. And I have a video. And then these are just a couple others. This is Qantas and Anadarko. This is Ocean Current Energy. But these are all the different things that they're developing to go out and harness the electricity. So what are the challenges that I have? After we've measured the environment and all this other stuff, what are the challenges that we have? So we're in deep water, right? I talked about that. It's a long way from shore. It's 20, 30 miles from shore. Continuous high flows. We don't get a tidal break like they do, in tidal flows where it goes slack and you can get a diver in real quick and do something and come back out. It's always running. The high flows near the surface, so you can't put a tower, and tropical storms, right? Big deal. So what are the advantages? Well, deep water, right? Because what's the scariest time on a plane for a pilot? Right near the ground, right? Because if you have a lot of space between you and the ground, you have space to fix things, right? And so if your thing starts to fall, you have time to address it. And you can also use things like lift-based equipment and stuff. Distance from shore, nobody can see what you're doing. No, just kidding. That's not it. That's not it. If that was the case, we'd only work at night. But no, distance from shore, you don't have small boats and a lot of the traffic and stuff, right? You're away from a lot of that stuff. And then continuous high flows, again, if you can count on that flow being there to use, as opposed to having to deal with it changing from 0 to some high velocity. Prime flows near the surface, okay, well, then we'll use kite systems, but again, we know that it's there, and then not tropical storms. They're bad for anything. And then just a few of the other really quickly, transport and deployment of these large things, how to control them, all the forces, how do you get the power back to shore? How do you put multiple devices on one cable, because the cables are like $4 million a mile, and then maintenance, repair, and then vessel traffic. And then just really quickly, this is just a nightmare scenario of all the forces that we have to deal with. Because remember, we have the variable velocity, right? So it changes. It's also higher near the surface. And we have all these drag loads, and on the devices, there's just all these different forces working against us. But know thine enemy, right? So if we know what is coming for us, then we can deal with it, and we can address it and design for it. And so that's what we've been working. Well, I've been working on. So this is our buoy that, remember, I had in our little cartoon. So, and this is just an example of some of the computer modeling that we do, where we take the 3D CAD model and we do add all the forces to it in the computer, and then we go out and test it, and we get a really good agreement between, at different velocities, the behavior of the device, right? And so once we put the buoy out, we're going to do what's called anchor last deployment, right? Remember when I put the ADCP buoy out? Except now, this is about 4,000 feet of wire, and there's about 80,000 pounds of chain that we're going to drop and then mount, and then moor the buoy. So you drop it from the surface, just like, remember I said, what? And I drop the buoy. Well, all the chain falls down. Meanwhile, the current, see how it's moving the buoy? And this is all computer simulated. And so it pulls tight, and then what I really wanted to see if it was actually mimicking real life is it starts to pull the chain out of this virtual pile that it made on the bottom, right? So it starts to do that, and the buoy takes the form that it's supposed to, and everything is cool. So that was a good verification. I can get loads and stuff and design everything. This is in real life. So this is when we were doing that buoy. It's a 50-foot diameter buoy in 6,000 feet of water. And this, see, when you're in charge, what you get to do? You get to dance with the devil, right? They're at about 8,000-pound anchor. Everybody else is 100 feet away with their cameras, right? Not me. And then you can see my shadow run along here, I think, in just a minute. We're getting the boat in position. Now you see my shadow. So this is 80,000 the whole chain falls, and then it pulls the buoy just like in the simulation. So that was pretty cool. Oh, thank you. I'm alive. Yeah, that's what we were really saying. All right, so this was the first version of our turbine. It's just an open rotor turbine. It just sits down in the water like you'd seen before. And this has some very heroic music, so I'll play this. Oh, here we go. You're going hunting a dragon or something. It's like. I'm telling you, man. If you want to stand up and salute, go for it. So anyway, we're taking this out. We're going to deploy it down and tow it behind the boat as to simulate the Gulf Stream. And we have cameras on it. And so you can see the rotor rotating in the back. You can see the ship from our upward-looking camera. And then you can see forward with the other one. Because we had to monitor for marine mammals as well. I just want a sword or something. So, here it is coming up over the stern. And you can see how easily it turns. When he turns a little bit of prop on, see how it really starts to spin again. This is a 3 meter diameter rotor, so we were looking to get about 15 kilowatts out of that at the final stage. We were just making sure it turned on this trip. But again, we're on the back deck, and Jimmy, and we're just having to bring this up. And you know, if you can see, this is almost as big as the size ship that we're using. We have equipment everywhere. So again, working on deck is a very important part of being an ocean engineer, is understanding how to do that stuff, so that when you spend all your time and money on something and trying to get it as good as you can, and then you're crazy enough to throw it in salt water where you can't go get it, right? And if it breaks, you're not going to get it. So that's the fine line of, that's the good thing, I guess. So anyway, that's our heroic effort there. So this is our new version. So again, if you only have one device on a cable, that's a very expensive thing to have. So we were looking at having multiple devices on it. Okay, this is a very early concept drawing. So we're looking at having multiple devices in it. The other thing is, if you put this on the bottom and you try to bring it up through all that high velocity, it's just going to tear it apart, right? It's like a genie in a bottle. Once you get on the bottom, getting it back up is going to be very hard, which will be another talk. But so we came up with this concept. We were sitting at a bar. I'm sorry, Mom, I didn't mean to say that. Anyway, and we were talking about it. I was like, well, what about a jukebox, right? Which you can't find a jukebox anymore, but I'm old enough to know what a jukebox was. So we put a coin in there, and it goes down, and it finds the right slot, right? And so what we did is say, okay, we'll make the generator like a coin, and as it comes down, it can either go there or there. And here's a little animation of it. So you lower it through the slot up here, right? Just like a jukebox, and it can either move there, or it can move there, or it can move there. And likewise, if one of these three breaks, right, something happens, you can eject it, take it out, put a new one in. Meanwhile, you're still generating electricity on this $4 million a mile cable. So you're continuing to generate, so it increases the resiliency of the entire system if you can change these out. So, and it's based on kind of, besides rum and coke, it's based on aerial refueling, right? And that's what we were trying to do. So these are starting to be the coin rotors that we're talking about. Remember, the other one was a 3-bladed rotor. These are more coin-shaped, so that they can fit in that configuration. And then we put them on our test barge here. And since there's going to be multiple, if you've ever been on multiple engine aircraft, they're turning different ways, right, to balance the torque. Because if they're turning the same way, you'll just spin yourself around. So the yellow goes one direction and the whites go another. And we were measuring and countering the torque difference between multiple generators too, because if one stops, you need methods to prevent the torque and everything. So we were doing this here. This is some of the electronics that we use for monitoring things. Now, the first part of this is going to be loud because I slide the camera. So just, oh, well, I guess I didn't, did I? Oh, there it is. Okay, that wasn't that bad. So this is the Harbor Branch channel, right? And so we put the rotors on front and we drive through pushing, simulating the flow. And this is the generator that we were using, a wind generator at the time, with a shaft and the rotors down below. And so we just push it back and forth at different speeds, measure the velocity, and it's the same as having it in an actual current. But we have one of probably the world's longest tow tanks now here at Harbor Branch because we're using the channel. But it works really well, and we can go out and can have controlled experiments on how well the generators and the props are doing. And then these are the guts of the ring generator, and then this is the first prototype. So this is a magnet ring. So instead of a normal generator where you have a shaft with magnets on it and it turns inside of coils, we have the magnets on the outside of this ring turning within a stator, and this is a 3D model that we printed just to make sure everything fit before we went out and built the whole thing. And so this is a video off my 20-year-old cell phone that's not very high quality, but this shows the tow stand that we lower it down, just kind of like an outboard motor kind of. We lower it down with a generator on front and we push it through the water. But that's the whole assembly there on one of our boats here. So once we quantify the actual rotor and generator itself, in order to make it work better, we're going to put it inside these cones called a flow conditioner. And so as the water comes in, it develops a low pressure back here and it sucks the water through. And that's our test setup that we're going to try on the barge if we don't flip it. And then this is using the Harbor Branch Ultra Advanced Tow Tank. So down at Fort Pierce Inlet, I went down to the fishing pier and I put a 3D model, printed model, into the water just to see how it would do. So everybody thought it was a fish trap or stuff like that. I was like, no, we're doing engineering here. So I stuck a GoPro in the water and I held the rope, and that's just to kind of see how stable this whole assembly would be, right? And so that's kind of like our small scale testing. So, and it worked all right, I guess. And that's it. That's my talk. Kind of abrupt, but sorry. So that's what we're doing.